This is where we ended last time, in the middle of talk 2. So we pointed out Post's theorem. Post's theorem says there's a correspondence between, so the Turing jump, the function, maps a set A to the complete sigma 0, 1 theory relative to A. So it maps A to the set of existential statements that are true about A, where the existential quantifier is a quantifier over natural numbers, or a quantifier over finite. And so there's a correlation, as you would expect, between definability and first-order arithmetic. First-order arithmetic is the formal theory of first-order language in the natural numbers. How do you build up formulas, Boolean combinations, and existential and universal quantification over natural numbers? So the jump is a computability theoretic analog of adding an existential quantifier, and then computing from the result. Okay, so the set is sigma n plus 1, so exists for all n plus 1 times, if and only if it's computably enumerable from the nth iterative of the Turing jump. Okay, so then we reviewed the Borel hierarchy. That's the standard thing that you see in measure theory. And then we started looking at a hierarchy of definability for sets of natural numbers, for countable objects, which is based on an ordinal-driven process. So to incorporate ordinals into the context of talking about definability for subsets of the natural numbers, you need a way to talk about ordinals. So you represent ordinals by a recursive linear order instead of isomorphic to ordinals. And then there's a systematic way to do that, and that was the system of notations for ordinals, script O, introduced by Martin Davis. And so script O, you start off with choose a representation for 0. For the ordinal 0, I chose 0. Choose a way to generate from a representation of an ordinal a representation of the next ordinal. So I, or Martin Davis, chose exponentiation by 2. And choose a way to, if you can specify an increasing sequence of ordinals, well, that specification of the sequence determines their limit. So how do you talk about the limit of a sequence? How do you talk about a sequence? Well, by a computable function. How do you represent how do you refer to the limit of 3 times 5 to the index of the recursive function? Okay, so that's a systematic way to generate codes for ordinals. Okay? Ways or names for ordinals. Now, if you have a way to represent a linear ordering of ordinal height, then you could talk about iterating the Turing jump along that ordering. So if you have some kind of ordinal, so you have some representation of 0, 1, 2, 3, 4, and then up here is omega. Okay. You can associate this with the empty set, the Turing jump of the Turing jump, the third jump, the fourth jump, and then up here you could put some kind of join of the nth jumps. And so this would be something like the set of n m such that m is an the nth jump. And so if you have a way to specify a sequence of variables, you can specify something that computes them all. Right? And the fact that you have a recursive description of how to get up to this height means you have a recursive way to index. For each n, you know what set to look at. Okay, so that's the, you have a code for an ordinal. You can define an iteration of the Turing jump of length, the ordinal that code refers to, and that means you specify for each b sitting in O less than a set HB. And they satisfy a kind of implicit property that H2 to the B is the Turing jump of HB, etc. That's a jump hierarchy. All right, then The finite levels of so that's called the arithmetic hierarchy. And what you get at each ordinal height depends on how you've represented. The set you get depends on how you represented that ordinal. There's many ways to define a subset of powers, there's iterative powers of 2. There's many recursive increasing sequences there. They all refer to the same ordinal omega, and they give you different ways to glue these sets together.
So if you, in the definition, if I remember correctly, you require, when you talk about the sequences, you require them to be increasing.
Yeah, that's right.
If you don't require them to be increasing, do you get a different notion, or is it?
Not really. No, because as long as they're ordered, the comparison map you can prove it's computed.
Okay.
The two things are notations for order.
So
you can enumerate which is small.
Okay.
It's for convenience.
Okay.
Okay, so the finite levels of the arithmetic hierarchy, namely these H sets, corresponds to the levels of the height hierarchy, corresponds to the levels of the arithmetic hierarchy. So this is an extension of definability and first order arithmetic. The H sets at the levels of the height hierarchy, if you would take a recursive, take an element of O and you put this jump hierarchy onto it, then what you get at the finite levels are just finite iterations of the Turing jump. All right, the H sets at the infinite level are equally computable with the first order degree arithmetic. Yeah, go ahead.
When you say the H sets, like, you need every H set to compute the first order theory then, or any one of them?
Any one of them.
Okay.
Any one of them. And then, because that could look a little ad hoc, right? That we have these different notations for ordinals, and we take a particular way to refer to an ordinal, and we associate some kind of jump hierarchy, right? And we stick a set there, which we're saying is the iteration of the jump up to that height. That calls for an immediate theorem. Right? If you have different representations of the same ordinal, do you get the same information? Or do you get sets that are equally computable? Or is it really dependent on how you represented the ordinal? And the answer is theorem that if this were not true, you'd have to change the definitions until you got it right. This is a target theorem. Right? If M1 and M2 represent the same ordinal, these two sets, what you think of as the ordinal iteration of the jump up to the height of M1, is the same as the set that you get if you represent the same ordinal by a different notation. Okay, so there's a degree invariant choice of sets at each ordinal height. And so that was proven by Martin Davis for ordinals less than omega squared, and then Spectre proved it for all the recursive degrees. And further, there's a uniqueness property. That's, when you define something like transfinite recursion, you're not really writing down an explicit definition. You're writing down an implicit property, right? That this thing has to be built up to satisfy that. The thing that you put in place 2 to the n is the Turing jump of the thing you put in place n, et cetera, et cetera. Right? And then you prove, and you have to prove by induction, right, that there exists these sets that satisfy the implicit property. Right? And usually in the way that you prove something like that the principle of definition by transfinite recursion is well defined, is you prove a uniqueness fact. There's only one way, there's a way to do it, and it's unique. That uniqueness calculation, right, is that each one of these sets is a pi02 symbol.
But I don't, what is O here?
O is the system of notations for ordinals. So this is the set of codes for ordinals. This is the set that you would associate with that notation, right, for as an iterative of the jump. And it's uniquely definable by transfinite recursion, right? And the uniqueness is at the level pi02.
Pi02 singleton?
It's a set that is the unique solution to a formula that forms for all n there exists n. Something bounded happens for x.
And then what does uniformly in M mean?
It means that the pi02 formula can be obtained recursively from M.
Oh, okay.
In a uniform way. So everything is although the representations of ordinals can vary, right, what it means to iterate the jump up to a certain ordinal height doesn't vary in terms of computable equivalence. They're all representing the same information, and you can easily translate between them. Okay.
And can you tell whether if I give you an M1 and M2, is there a way to tell whether they represent the same ordinal?
It's a hyperarithmetic problem to tell whether they represent the same ordinal. To represent an ordinal is a pi11 complete property. So it's a very complicated set. If you have two things that are in O, then it's to tell that one of them represents something less than the other is also a pi11 complete. Then you have to work your way up to the ordinal height by iterating the jump. You don't see the ordering until you get a set this complicated. To tell that one of them is below the other in O, in the system of notations, that's easy. That's to tell how to compare their ordinals, that's complicated. All right, so there's a theorem of spectra. So we have this system of notations for ordinals. Suppose that you have a sigma 1,1, so that sigma 1,1, remember, exists a real such that some pi01 statement is true. Okay, so it's an existential quantifier over countable sets. So suppose you have, that's a fairly complicated definition. It's a lot more complicated than sigma 0,1, where the quantifier is over natural numbers. It's more complicated than arithmetically definable. It's even more complicated than recursive in any one of these H sets. Okay, so suppose you have a sigma 1,1 subset of O, then the supremum of the ordinals represented in S is strictly smaller than omega 1 ck. You can't, in a sigma 1,1 way, pick out a collection of notations for ordinals which is cofinal in all the recursive ordinals.
Is this also called the Kleene boundedness theorem, or is that something else?
It's called the spectre boundedness theorem. Yeah, so Kleene used it in a theorem that I'm going to cite next, but Spectre proved it. So this has an interest. I'm putting this one up. I mean, I was going to, because I'm taking longer than I expected. Right, I'm omitting some of the proofs. Oh, but my original slides should go up this afternoon, which include proofs of some of these theorems that I'm omitting in the lecture. So if you are curious, you can look at the slides and see the proofs.
Sorry, what's omega 1 ck?
It's the least ordinal which is not isomorphic to any recursive linear ordering of the natural numbers.
Omega 1, but what's the ck? The
Church Kleene.
Oh, so it doesn't mean it, it's just omega 1.
It means omega 1
In
in the recursive sense. It's
yeah.
the least uncountable ordinal. Okay. The countings have to be recursive.
Yeah.
Right. Okay, so suppose you have a... What?
For its non-computable ordinal.
Yeah.
Yeah, I've not seen the ck superscript before.
Okay.
So sigma 1,1 subset cannot be a path through Kleene as well.
Correct, yeah.
Okay.
Okay, so now, it can't be complete of cofinal range. Okay, so this has an interesting consequence. It tells you that O itself is not sigma 1,1. Right, so this is a different kind of proof that there's a pi11 set. O is a pi11 set, which is not sigma 1,1. It's not I don't see this as a diagonal argument. It's a structural fact, which implies that there's a pi11 set, namely O. O is something about being well-founded. There's a pi11 set, which is not sigma 1,1, and it's not by self-reference. It's by a structural fact. So those sorts of things I find them quite, they're interesting, right? It's not a syntactic argument; it's a structural argument.
Do you think the proof is not the diagonal argument?
Yeah, no, the proof is not a diagonal argument. The proof is an analysis. It's an ordinal analysis. Yeah, so you can sort of see it. It's like if S is sigma 1,1 and it's contained in O, then for every natural number, either it belongs to O, or it doesn't belong to S. Every natural number has then a well-foundedness property, and you can bound them all. That's how the proof goes. It's similar in, well, okay. Okay, then this corollary, this head O is a pi 1 1 subset of n. It's not sigma 1 1. And you don't need Spector's bounding theorem to prove that there's a pi 1 1 set that's not sigma 1 1. The usual diagonal argument will work. If you get into it a bit, O is a complete pi 1 1 set. The complete pi 1 1 set by diagonalization is not a sigma 1 1 set. A more say, canonical or natural pi 1 1 set would be the set of computable well orderings of the natural numbers. That's also complete pi 1 1. So there are natural complete pi 1 1 sets. Being a well ordering is a natural property. Okay, so then one important application of Spector's theorem was this theorem of Kleene. And Kleine's theorem says that a set is hyperarithmetic. So that means a set is hyperarithmetic means that it is recursive in one of those H sets. So X is hyperarithmetic means there's a recursively presented ordinal. If you iterate the jump, that ordinal many times, right, you can then compute X. Okay, so that's what height means. That it's something that is computable computable from recursive iteration of the Turing, recursively presented ordinal iteration of the Turing jump. Okay. And so a set is hyperarithmetic if and only if it's delta 1 1. So let's pause for a second. Right? If you're given a delta 1 1 definition, what does that mean? It means that n belongs to the set if and only if there exists a real that has some nice pi 0 1 property. And n does not belong to the set if and only if there exists some other real that has some other pi 1 1 property. There's no internal structure given in this way of specifying a form of a definition. Just like there's no internal structure that's given by saying a set is recursive. A set is recursive means there exists a witness that there exists a computation that the number's in, or there exists a computation that the number's out. That's a recursive set. There exists a real that says it's in, or there exists a real that says it's out. That doesn't come endowed with an internal structure of the sets that are so definable, whereas this does. The hyperarithmetic sets have an internal structural ramification of complexity. I don't know anything like that for the recursive sets. Recursive is a blob of sets that are all computable. We don't build them up, from the successor function by a sequence of much less complicated operations. They get built up by the least number operator, which just swaps everything. Okay, so there's an interesting development here that is sort of unprecedented. Okay, so very nice theorem of Kleene. Okay, this also has a nice, I don't want to spend too much time, but let me point out something which I find very exotic, right? Which is, suppose I have a computable linear ordering of the natural numbers. Okay? If it's a well ordering, then it supports a jump hierarchy. In fact, what do? You do exactly what I described here. At successors, you take the jump, and at limits, you just join together everything that you had below and stick it at the limit point. Any well ordering of the natural numbers would support a jump hierarchy. You just keep iterating the jump and pulling things together. Okay. Now, so if you have a recursive well ordering, it supports a jump hierarchy. Okay, and there's the internal definition of what it means to be a jump hierarchy. Okay, so the condition that each recursive linear ordering supports a jump hierarchy is the sigma 1 1 property. There exists this assignment of reals to integers which satisfies those recursion properties. Sigma 1 1. The holds of every every well-founded recursive linear order. But being well-founded is a complete pile of one property. It can't be the case that supporting a jump hierarchy, right, defines being well-founded, because that's not a signal on one set. So there are non-well-founded linear orders that support jump hierarchies. Exotic jump hierarchies where they start off in a nice way, but somewhere in the middle, it's not well-founded anymore. So it's a hierarchy of definability where at some point it has no bottom. It's the jump. You can keep going down by the jump.
What do you mean by, what are the conditions of causing the jump?
Right there. The least number has to be assigned a set. It has to be assigned a set, the empty set, and if you're the successor of a point, you have to be assigned the jump of your predecessor, and if you're a limit, you have to be assigned the join of the sets that are assigned below you. It's the recursion properties. And if the order is well-founded, there's a unique thing that satisfies these recursion properties. But there are non-well-founded jump hierarchies that are very exotic. And there's even more, you can get even more exotic structures. You can get models of set theory in which the natural numbers are standard. I mean, this isn't a first order compactness conclusion. And actually you omit the type of a non-standard integer. But the orders are not well founded. In fact, you can find such objects recursive in the complete power one set.
What is the definition of well-founded?
Well-founded means, so for an ordering, it just means every subset has the least element. No infinite descending sequence. Yeah, go ahead.
So if you have this pseudo well-ordering and you make a jump hierarchy based on that, is there a notion of pseudo hyperarithmetical? What kinds of natural numbers do you get?
Well, so you could, what kind of natural numbers?
So, sorry, what kinds of sets of natural numbers do you get?
Yeah, so the sets that you get, every one of these non-well-founded jump hierarchies has to compute all the hyperarithmetic sets. Something that's in the non-well-founded part is above all the hypersets. But other than that, you can get such things recursive in claims. You can even like Gandy basis theorem. They can all have the property that their complete power one set is recursive and so you don't get things that are really complicated, but they're more complicated than height. So they go beyond height. Okay, and these non-well-founded, so if you thought like there has to be a model theoretic thing going on here, we're getting interesting structures, right? That are omitting certain kinds of types. You get a jump hierarchy that omits the type of a non-standard integer. So there must be some kind of model theoretic insight here. And the answer is that there is. And these were the germs that set off Barwise compactness theorem and things of that sort. Okay, so what do you get beyond height? So this is a canonical example of a theorem that transcends what you can get, what you can capture by the height hierarchy. It appears, right? Its complexity, the complexity of this kind of argument appears at the level of pi 1 1. Okay. So you're trying to get interesting examples at each level. So this is the Cantor-Bendixson theorem. Suppose you have a closed set, and it's written, then you can write it uniquely as the disjoint union of a perfect set, that's a closed set with no isolated points, P for perfect, and a countable set. That's the Cantor-Bendixson theorem. Every closed set can be decomposed. If you have an uncountable closed set, it has a perfect subset, and in fact, throw away that perfect subset and you get, if you pull out a countable, this is a unique thing. Okay. What's the proof? So I'll show you two proofs. The first proof is very short. So I'm not doing uniqueness, I'm just doing, how do you define P? How do you define this perfect subset? Here's the first. P is the set of X such that every neighborhood of X has uncomplementary elements in C. Okay, that's it. Okay, now how hard is this definition? Well, can you talk about uncomplementary elements of C in first order arithmetic? Well, no, this is way beyond an existential quantifier over finite. Can you build it up from the halting problem or the halting problem of the halting problem or something like that? Well, even that, that's all iterations of first order number. So this goes beyond that. This is not formulated in any of those languages. This is in the realm of quantifying over subset of the reals with the property of uncountability built in as a primitive. Okay, so this is not an effective presentation of the set. Right? Okay. But here's the way to define this. The second way to do it is this Cantor-Bendixson, probably the more familiar argument, is that you define C by a transfinite recursion. You start off with, you keep throwing things away, right? Trying to winnow down to the perfect set. And the thing that you do is you start off with C, you look at all the isolated points that C has, remove them, and then iterate until you hit a fixed point. That's this Cantor-Bendixson derivative. Right? And if you do that countably many times, you will hit a fixed point at some countable stage. Okay. All right. Now, one. It's not even so obvious that this is true, but if C is countable, right, this process will eventually terminate. And in fact, it terminates at an ordinal that's recursive in the presentation of C. If C is not countable, well, Kreisel, this is the contrarian who wrote the review. Yeah, he's a famous contrarian, this guy, George Kreisel. Probably this is the most interesting part of the talk. My thesis advisor was Gerald Sachs, and he and Kreisel. Kreisel was a very influential guy who didn't write that many papers, but he talked to a lot of people. And he had he sort of, he asked interesting questions, and he had an interesting vision as to problems that one might pursue or try to understand and how that might happen. And so he worked with various people. Every person that he ever worked with eventually became his mortal enemy. The only people that he didn't become mortal enemies with were the people who were willing to talk to him a bit and then leave the room before things went south. So the story that I heard about him was he was giving a talk, and in the context of, maybe one shouldn't speak ill of those who have gone before us, but this is just an account of fact. So you can form your own judgment. So he's giving a talk and question. And what is your question? Kreisel was talking about this kind of topic, and the question is, if you're going to talk about this, shouldn't you also mention that? Kreisel said, no. That is not my interest in this talk. And then he continued. And then a few minutes later, the hand went up and Kreisel looked and said, what is your question? And then the same person said, but that is very important here to understand such other thing. And Kreisel said, such other thing is not the direction I'm going. I have no interest in such other thing. Starts to talk again, the hand goes back up. And then, now with the punchline, right? Get ready. Kreisel looked at the hand, looked at the person, looked up and said, a man who stops to listen every time a dog barks never reaches the end of the street. It was dead silence for about 10 seconds. And then in the back of the room, Michael Morley, a well-known model theorist, goes, ha, 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 ha. And then there was a twitter of embarrassed laughter. And no more questions. So it's not surprising that he would write a review of the sort that I mentioned. It's unlikely that this will lead anywhere. But I said, okay, so that's why I say famous contrarian. Okay, but he did point this out. There's a computable tree, even with no dead ends. There's a nice recursive tree sitting inside the Cantor set, such that it has uncountably many paths. So the paths through a tree are a closed set. So there's a recursively described closed set. It has uncountably many elements, but it has no hyperarithmetically presentable perfect subset. So the Cantor-Bendixson theorem takes you out of height. If you want to prove that decomposition theorem, you have to use objects that are not hyperarithmetically definable in general. And all you need is the complete Polynomial set. Okay, so the Cantor-Bendixson theorem and other kind of ordinal-driven constructions sort of sit at the level of Polynomial. All right. Now, I want to mention this theorem, and then I'll follow up on it. There's Sussman's perfect set theorem, which is a generalization of Cantor's theorem. Sussman showed that suppose you have an uncountable analytic set. So analytic set, remember, is the projection of a closed subset of the plane. If you're with some technical, it has to be a plane that involves bare space or something. So an analytic set, suppose you have an uncountable analytic set, then it has a perfect subset. Okay, so the uncountability of analytic sets resides on their closed subsets. That's Sussman's theorem. And then I want to mention this nice application of the things that we were just discussing. There's a theorem of Gaspari, Kekers, and Sachs independently. So if you work in Gödel's universe of constructible sets, which means what was Gödel's idea? He took this idea of iterated definability, right, and just iterated definability and never stopped. Right? So it's a first order operation. You start off with the empty set. Then you view the empty set with the epsilon root. There's not much to this structure. Right? One relation symbol, epsilon, for membership. You start off with the empty set, and you look at every set you can define. Okay? There's one set you can define, namely the empty set. Okay, so now you look at now you've got all the definable sets, right? So now you've got a set that has an element. Then you look at everything you can define. Then you look at everything you can define over that, and everything you can define over that, and iterate that process. At step omega, you've got the hereditarily finite sets. Step omega plus 1, you've got arithmetic. Step omega plus 2, you're working up the height hierarchy. Right? Go through all the ordinals. That's Gödel's universe of constructible sets, the sets that necessarily exist because they're built from nothing by ordinal transfinite recursion. Inside, that's a model of set theory. It's the ultimate, like everything is there for a reason view of the model of a model of set theory. So Gödel proved that the generalized continuum hypothesis works there. The axiom of choice is true there, fiat basically, because every set there's an order of construction. Well ordering of all sets by order of construction. Okay, so look at this set, the set of real subsets of n, such that X can compute the ordinal which it's constructed. So these authors prove that that set is pi1, 1, right? And it's uncountable because, well, you have to prove that. Okay? And it has no perfect subset. So Sussman's theorem, in the sense of provability, is optimal. Namely, every analytic set, if it's uncountable, is a perfect subset, but it's consistent with the axioms of set theory that there's a co-analytic set built up by this kind of computability theoretic insight, which is uncountable, but has no perfect subset. All of its closed subsets are countable. Interesting that computability would address issues raised at that level of definability. Okay, so we'll move on to the next topic. But before I do, any questions? Jokes? Anecdotes? Okay, I'll handle the jokes and the anecdotes. Okay, so that's the end of talk 4. Talk 3. View. Okay, so I want to talk about the question of these hierarchies of definability. Do they have, that we have explicitly defined them, do they have sort of intrinsic, can we identify intrinsic properties that they satisfy, which can't be satisfied in any other way? So is there, do they really fill a niche? Right? Or are they kind of ad hoc? The way we represented ordinals was completely ad hoc. So, do these things, are these things sort of intrinsic, or do they, are they one way to do it, but there's many different ways to do it, and we just happen to choose one. Okay. The topic of this talk is an attempt to pose that question in a mathematical way so that we might be able to get some mathematical evidence on that. And it's nicely captured by this thing called Martin's conjecture. Okay, so to set it up, I need to introduce some additional notation. So for A and B, subsets of the natural numbers, A is above B in the sense of Turing, if and only if, oh, I wrote that wrong. B is computable relative to A. A can compute B. Well, I shouldn't get that one wrong. Okay, so A is above B means A has more information than B, where the information in B is embedded in A. So if you have A, you can compute B. The partial order of Turing degrees is the set of equivalence relations, and the equivalence classes have an induced ordering from computability on their elements. And so we're going to identify two sets if each can compute the other. And then we say that the degree of A is above the degree of B if anybody that can compute A can compute B. Okay, that's a kind of structure of relative computation. We're trying to throw away all the issues of representation and just look at the ordering of information, degree of information. So D is a natural join. That means any 2 points have a least upper bound. You can glue together the information of A with the information of B by putting A on the even part and B on the odd part. Okay, here are some of the things that are known. If you want to understand that structure, the theory of the Turing degrees, well, it has the same first order theory as second order arithmetic. And so it's the theory of D goes beyond pi 1, 1, it goes beyond sigma 1, 2. It's full analysis. You have to know everything that's true about arithmetic on subsets of the natural numbers. Okay, second, this business about relativization. So lots of the things that we've seen where you can do, the notion of X is computable can be relativized to the notion X is computable from A, or X is definable from A. X is hyperarithmetic to X is Borel at that ordinal level. And so that business of relativization, though, does not fully transfer over. There are degrees A, such that if you look at the Turing degrees and you compare that to the Turing degrees above A, the Turing degrees relative to A, they're not elementarily equivalent. So there are inhomogeneities in the Turing degrees, which
what is this? I'm not parsing it right. What is it saying?
it says that there is an A, there is a degree, such that the partial order of D, the partial order of the Turing degrees is not elementary equivalence to the partial order of the Turing degrees above A.
Oh, this is, okay, so D is,
D is the Turing degrees. That's the partial order.
That's a pretty clear.
Yeah, so
And then this is,
when I write D, I'm thinking of it with its partial order structure.
okay, and that last thing, that last line, that's just the notation for
The degree,
cutting off
right, the degrees of the
stuff about.
only look relative.
Okay.
And so there's an inhomogeneity. There are things that don't relativize. Properties of degrees that don't relativize. Yeah, go ahead.
Would you mind saying a bit about, even from the purely abstract standpoint, what are properties of A that make this?
Yeah, so it's if you take, well, let's see. So briefly, and I'll get more to this in a second. Briefly, the things that can compute A, right? Like suppose that A is the theory of true arithmetic. Well, those degrees anybody who can compute true arithmetic can do all kinds of arithmetic constructions. And it can build complicated objects. Those complicated objects can interpret models of arithmetic, or models of arithmetic with a predicate, or the set that is driving the construction. So that being sufficiently complicated means that you can compute things whose order relations with each other is very complicated. More complicated than what you can do without A. And that's the source of the inhomogeneity. But there's much more inhomogeneity than that, which I'll say in a second. The next thing is sort of some evidence that yeah, go ahead.
So you said the first order theory of D is completely isomorphic, the second order theory then, you say we're thinking of D as a partial order?
Correct, yeah.
What is the partial order structure on the second order theory of N?
Well, the second order theory of N is take first order arithmetic and have also quantifiers over sets.
No, what's the order?
What's the order?
No, it's different structure, it's different language.
Different language.
Yeah, the theory is computably isomorphic, not the structure.
Oh, computer, so, okay.
So if there's a way to translate between a statement about second order arithmetic to a statement about
Okay, there's not a computable isomorphism between the orders.
between the theories. The first order theory is completely isomorphic to the second order theory.
Ah, okay.
Okay, so it's that you can say this statement is true in second order arithmetic if and only if this recursively obtained statement is true in the Turing degrees. It's a statement about the theories. Okay, so the next one is some intrinsicness, maybe. So the Turing jump is definable from just the order of the Turing degrees. So the jump is an operation of representatives. There's no reason to think a priori that it's definable just from the ordering between degrees of information, but it is.
You have another question?
Yeah.
Does D also contain the Turing degree of computable sets? Or do they
Yeah,
not?
0, that's the least element of D. Right. So D has a least element, the degree of the computable sets. Every set can compute a computable set. Okay, and then finally there's a whole raft of theorems. I will just point out the first one. If you have an automorphism, this is an interesting problem. If you have an automorphism of D, this is an uncountable. The Turing degrees are the reals, or the power set of the natural numbers, mod a countable equivalence relation. That's an uncountable structure. You would expect that its automorphism group could be huge. Right? By cardinality arguments, it could be gigantic, like more than continuum. Right? But actually, you can prove that the automorphism group is countable. And every automorphism, first, it's open whether there's a single automorphism. There is a single automorphism, the identity. It's open whether there's a single non-trivial automorphism. Okay, so not knowing whether there's a non-trivial automorphism for a large uncountable structure, you can prove that the automorphism group is countable. And the way you prove it is you show that if you have any automorphism at all, it's represented by an arithmetically definable operation on representatives. And there's only countably many, so if you have an automorphism at all, it's simply definable, which gives it the group is countable. So you get a weird way to show that a group is countable without exhibiting any generators. It's a quite interesting situation. And then it's rigid, it has only the identity as an automorphism, and only if it's bi-interpretable with second order difference. Right? So the conjecture is that it's rigid, and the fact that the jump is definable is just a special case of everything is definable. You can define it in second order arithmetic and its degree invariant. You can define it strictly from the order. So we're in an interesting state of partial knowledge with what we know and what we don't know. And then the question out of this is D rigid? It's one of the fundamental.
Rigid means automorphism group is trivial.
Right. Rigid means no non-trivial automorphism, exactly.
And can I ask, relate to Shor's result, if I take a particular A, like I don't know, zero jump or something, are all obvious A's like that? Do they fail this condition?
It's, let's see, so for the degrees above.
I'm wondering, are there non-trivial A's for which D is elementary equivalent to D the
Let's see, there's non-trivial A's, there are non-trivial pairs of A where you have elementary equivalents. In fact, for all sufficiently large A, the theory is fixed. So there's a cone on which they all have the same theory. But whiteface, I think that's okay. Whether there's some particular A which is such that D greater than or equal to A is elementary equivalent to D. As far as I know. Yeah, I'll think about it some more and see maybe I can think of an example, but I can't think of one right off. Yeah, go ahead.
There's a cone where the theory is fixed. Is that the theory is distinct from the theory of whole theories?
Yeah.
Is it known then, so Shor's theorem holds on a cone? Okay, thank you.
Okay. But let me. Yeah.
So regarding the automorphism group, where is the gap in Hoover's proof?
What's the gap?
Yeah.
It's wrong. It's one of those proofs where there is no proof. It just fades to fog. And so it's hard to point it. Have you ever read a document where the definition is a little vague, but you got it pinned down to two possibilities. It could mean this or it could mean that. And then the next definition is a little vague, and depending on the first one, it could mean this or it could mean that. And now you've got 25 definitions in a row. And QED. Anyway, that was my experience with it. Okay, so now, I want to get to this, the results on...
You remember he gave 9-hour talk 3 days in Oberwolf?
I remember that, yeah. We don't have to rehash all of them. I don't want to speak the whole bit. All right, so Martin's conjecture is an attempt to look inside the Turing degrees or functions on degrees. It's stated in the context of the axiom of determinacy. So, first off, the axiom of determinacy is true for all the sets we're talking about. It's true for all the Borel sets. So it's not some wild-eyed fantasy. It's something that's true for definable sets. That's a theorem of Tony Martin's. Okay, so it's a way but it gives you a principle that lets you prove existence facts. Right? It's got a very powerful way to prove existence theorems. Right? So it's stated in the context of games. Suppose you have a set of a subset of Baire space. Right? So that's an infinite sequence of natural numbers. Okay? It's a set of subsequences. Okay? There's a game that one could play. Right? I'm going to play against Bjorn, and Bjorn's going to win. So the game is, I choose a number, he chooses a number. I choose a number, he chooses a number. We play infinitely many numbers. It's perfect information. We each know what the other's doing. We don't know what the other's thinking, right? But we know what the other does. Right? And after the sequence is completed, we check membership in A. And I'm playing to have it out, and he's playing to have it in. If it's in, he wins. If it's out, I win. Okay? So that's the game. You alternate building an element of bare space. And the strategy is like, I've seen finitely many steps. It's my turn. Look at my strategy. Play this number. Given that the game has evolved this way, play that number. Whatever the response is, check the strategy. Play that number. Okay, so a strategy is a map from finite sequences to numbers. It tells you what to play next. The axiom of determinacy says every set has a winning strategy for one of the two players. There are no games where, it's like a fair competition and it's a match of skill. Every game is determined. That's the axiom of determinacy. Okay? It's true for all Borel games. It's a really nice exercise. Do it yourself for closed games. Okay? And the clue is don't lose. Play not to lose. Okay, so all Borel games are determined. Now, why is that a way to prove existence theorems? All you have to prove is that your opponent doesn't have a strategy. Oh, then suddenly you have one. You don't have to say what your strategy is. It just exists. It's like I prove existence by getting a contradiction that some other thing exists. That's a very powerful proof method. You don't have to know anything about the thing that you can conclude exists. Right? It's just, the opponent can't win. I wish life were like that.
So this function, the sigma, it doesn't have to be computable in any sense. It can be
No.
an arbitrary function.
Correct. That's right. That's right. And they are extremely complicated. As you go up the Borel hierarchy, those things are extremely complicated. So there's an interesting side theorem of Harvey Friedman's. Tony Martin's theorem cannot be proven in the system of set theory, which involves only countably many iterates of the power set of the reals. If you want to prove this theorem, you need uncountably many iterates of the power set of the reals. And the strategies, of course, are correspondingly complicated. So it's a real dig into meta-mathematical methods to prove this theorem. But it's just a theorem that proves the existence of sets of natural numbers. All right, so now, consequence of AD is that a cone, right, is a set of, there is a B, such a cone is everything above B. If you think of the ordering as going down, getting simpler is going down, the Turing degrees are some blob like this, and zeros at the bottom, the degree of the recursive sets. And a cone is everybody who's sufficiently large, everybody above B. And under AD, or if you want to put Borel sets A, every set either contains or is disjoint from a cone. So the cone filter is an ultra filter under AD. Yeah, go ahead.
How strong are these cardinals?
How strong are cardinals? Up there. Yeah, so they became known as wooden cardinals.
Okay.
So I think you need the consistency is at the level of omega many wooden cardinals, and the truth is omega many wooden cardinals with a measurable above or something. Okay. Now we're ready for we're essentially ready to state Martin's conjecture. So we're going to talk about functions from sets of integers to sets of integers. They are Turing invariant, means if x and y, if two arguments are equally computable, the two values are equally computable. So it's like a Turing jump. If x and y can compute each other, then the jump of x can compute the jump of y, and conversely. Okay, so that's the identity. The identity is a Turing invariant function. If x and y can compute each other, then x and y can compute each other. Any constant function is degree invariant. If x and y can compute each other, then c can compute c. Turing jump, the double jump, all these hyperarithmetic functions. That's what we prove with Spector's theorem. If you iterate the Turing jump omega squared many times, doesn't matter how you do it, you get things that are equally computable. Okay, so We're going to talk about Turing invariant functions. Those are functions that you could think of as mapping x to some universal set for a notion of definability relative to x, like the jump, or the theory of arithmetic, or the complete power one set, or anything you want to think about. Okay, then we're going to order functions by just saying let's order them pointwise on a cone. Two things. G is above f if and only if for sufficiently complicated arguments x, g of x can compute f of x. So the Turing jump is above the identity. The identity is above any constant, and so on. All right. Theory of arithmetic is above all finite iterates of the jump, and so on.
What does th and comma x mean?
Where are we?
At the right end of your chain of.
The theorem.
Oh, this is the theory of the natural numbers with x as a predicate.
Oh, okay. So, okay.
Okay. So the complete power one set relative, the complete sigma 0 1 set relative to x is the existential part of this theory. Okay. All right. So Martin's conjecture is under AD, or if you want for Borel functions, if you're not above the identity, if you have such a degree invariant operation, it's not above the identity, then it's equivalent to a constant. There is no way to go from x to something that's incomparable with x, for all x. Yeah, go ahead.
The n equivalent to just less than or equal to on that, not many one?
Let's see, so this m is less than or equal to m is defined up there.
Yeah, okay, so it's the same. I thought it was the same one for a second.
No, it's the same, this is the same ordering up there. So if you're not, if f of x is not above x in complexity on a cone, the conjecture says f of x must be constant on a cone. So if it's not above the identity almost everywhere, it's constant almost everywhere. And the ones that aren't above the identity almost everywhere are pretty well ordered for this ordering, and the successor of any function is its jump. So there's the identity, and then there's nothing above the identity that's not greater than or equal to the jump. So the jump is the least degree invariant function, right, that increases information.
What's pre-well ordered mean?
Pre-ordered, well, you can have two functions. It means that
It means
it's a
they
less
are
than or
equal.
equal. It's a less than or equal.
So does it mean that the equivalence classes for this
The equivalence classes
for this
right,
partial order are well ordered?
Correct. The equivalence classes, if two things can be equivalent because each is above the other, if you collapse that, you get a well ordering. And the well ordering is driven by the existential quantifier over finite. There's no way to go to the side. There's no way to go in between. The jump and its iterates are the only ways to operate on reals and change information. Or you can be constant, or you can be some iterate of the jump, and that's it. Okay, so now, I said that with great force. It's just a conjecture. It could be wrong. It could be completely wrong. But it is a way, I would say that this conjecture, right, is a nicely formulated mathematical assertion or conjecture, right, that the hierarchy of definability we've been talking about is intrinsic. It has an implicit property. Right? It's a degree invariant thing. Right? And it fits in, and all the degree invariant things fit in this, they're ordinal parameterized. And the only way to go up is by the jump. Okay. That from the point of view of saying it looks intrinsic, this says it looks intrinsic. Yeah, go ahead.
So given that we know that they are low Turing degree, so you for Turing degree cell, you might not, they are things that lower than jump. Why is it more plausible here that
Yes, it's because if you try, so there are many different ways to construct degrees recursively in 0 prime that are between 0 and 0 prime. You can do it, we mentioned the Jakob-Sauer theorem. You can do it by a compactness argument. You can do it by a bare category argument. You can do it by a measure. You can build something that looks kind of generic. You can build something that looks random. You can do it by a measure theoretic argument. You can do it by a direct enumeration and a diagonal argument. But those things all depend on the order in which you do the tasks. How do you meet certain kind of dense open sets? In which order? Right? The order that those constructions use is the order of the listing of Turing functions, right? The listing of programs. They depend on the presentation of what it means to be computable. You permute the order in which you take the steps of your construction. You change the degree of the object that you build. And the degree in this thing, that the F has to be degree invariant. It has to be that if you're given two different representations of the information in X, you have to give two different representations of the same information in F of X and F of Y. None of those constructions are degree invariant. At least all, prima facie, they're not degree invariant. The problem is, can you convert one of them into something that's a degree invariant operation? Okay, so now.
So why is there an assumption of AD here? Is it easy to disprove?
This conjecture is false in now.
Is that easy to see, or is it?
Yeah. So one example inside L would be to map f of x goes to x if omega 1 of x is a successor admissible, and f of x goes to x jump if omega 1 of x is a limit of admissibles. So, or etc. I mean, there's lots of examples. And then you can do an axiom of choice. You can do an axiom of choice construction to get a counterexample too. But with the axiom of choice, you could choose a representative of each degree, and then you just let f of x be some ad hoc construction according to that representative. Okay, go ahead.
Is the essence of these counterexamples like non-measurabilities?
Sorry, say it again.
Do you have a non-measurable set of degrees and you build the counterexample?
Yeah, just if you're in the set, f of x is x. If you're out of the set, f of x is x jump. Okay, so here's what's known. The evidence, I mean, the conjecture is open. The evidence is uniformly in support of the conjecture, except for the fact that nobody's proven the conjecture. That evidence, right, is not in support of the conjecture, but all the theorems are in support of the conjecture. So the first theorem is if you look at functions that are degree decreasing, like looking at x and writing it as equivalent to g jump, like in the Friedberg jump inversion theorem. Right? A way to look at x and produce something non-trivial, well, whatever, to be trivial. Look at x and try to find something simpler. And that's this. The identity is below that. So if you're trying to reduce information, go from x to something less complicated than x, you can't do it. The only way to do that is to be constant on a cone. If AD holds, or if you're talking about Borel F, where AD is provable. So there is no degree invariant inversion of the Turing jump. No Borel way to do it anyway. So Mark, that's the one kind of direct verification of the Mark conjecture, that case. The second case is that Mark's conjecture is true. It's true in full. If you require an additional uniformity in the way that the function is degree invariant. Uniformity just means that you have some way, if x and y are equivalent and you know how x and y compute each other, then independently of x and y, you know how f of x and f of y compute each other. That's uniformity. Right? So the way that degree equivalence is transferred by f can be specified independently of the arguments. Now the Turing jump has that property. how do you do it? If you know how x and y compute each other, or you know how x and y can simulate each other's computations, so then you know how x jump and y jump compute each other, if you, et cetera, et cetera. So all the examples that we know of degree invariant functions are uniformly degree invariant on a kernel. Right, so the conjecture is that every degree invariant under AD, every degree invariant function is uniformly degree invariant. That's open, but that's the conjecture. And it's uniformly degree invariant means it's represented by a uniformly degree invariant function. It's equivalent to one. And if that conjecture is true, well, clearly Martin's conjecture is true too. If Martin's conjecture is true, it's most likely that every equivalence class is represented by a uniformly degree invariant function. So if we add a little bit of additional constraint, the Martin conjecture is just true. That's, I think, reasonable evidence for Martin's conjecture.
Well, what about restricting to definable functions in D?
Well, let's see. So if they are represented by Borel functions, then we're in the context of its class. Definable in D. Yes. Now, okay. Let me. Definable in D. Well, that's in the realm of second-order arithmetic, right? Because quantifying over D is a quantification over Turing degrees. That's equivalent to a quantification over reals. Okay. Now, if you assume enough large cardinals, right, then you have the axiom of determinacy for all such, those are called the projective sets. And projective determinacy is provable from modest large cardinals, but it does require some additional assumptions beyond ZF. But those things will fall under this with some meta-mathematical consideration. Okay, so then the last one is Martin's conjecture holds for order-preserving Borel functions. Order preserving just means instead of saying if you know how if x and y are equivalent, then their images are equivalent. Order preserving is that if x can compute y, then f of x can compute f of y, like the Turing jump, or theory of arithmetic, or all the other functions that we know that come out of universal sets for definability. Okay, so Martin's conjecture holds for order preserving Borel functions. It's not known whether AD implies Martin's conjecture for order preserving functions at large. And a really beautiful recent result, Lutz and Siskin, part one, if you're not above the identity or constant, holds for all order preserving functions. Okay, so sorry, I wanted to catch up and cost you 8 minutes. I won't give any proofs, but we put the slides up. There is a sketch of a proof of this for the first level, at the level of the Turing. Okay, thank you.